Welcome to PhiPsiPi. Intuitive idea. In mathematics, we write stuff like 1 is less than 2, 2 is less than 3, 1 is less than 3, or 1 plus 1 equals 1000, 8000. Notice that we can assign truth values to all of these sentences, and that's why they are propositions. But we also can combine them and say more complicated things such as 1 is less than 2 and 2 is less than 3, 1 is less than 3 or 1 plus 1 equals 1000, 8000. And even if 1 is less than 2 and 2 is less than 3, then 1 is less than 3. Be aware that these are also propositions, but they are more complex, and that's because they are made of simpler ones. So in mathematics, we call connectives to the symbols that allow us to connect propositions and express a new one. If you study carefully the propositions in English language, you'll notice that you only need 4 connectives to express them all. Let's see quickly how we might test this. Think of the most common conjunctions that you studied when you were a kid. And, nor, but, or, yet, so, however, therefore, hence, nevertheless, except for. Now build a sentence using that conjunction. For example, cats are good pets, but dogs are better. This can be written in terms of and in the following way. Cats are good pets and dogs are better pets than cats. You might feel that the meaning changes a bit, but the important logical part of the message remains intact. Besides, our final objective in these videos is to actually do math, and the word but won't be that useful when dealing with truth values. If we really want to say that dogs are better pets than cats, we only need to assign a number to each set of animals and compare them with the symbol less than. Another example would be, neither Wally nor Eva are humans. This can be changed to Wally is not a human and Eva is not a human. Again, you might feel there's a tiny change in the meaning, but the truth value of the first sentence will always be the same as the truth value of the second sentence. Now let's start formalizing these ideas. Formal idea. We are going to study how truth values behave if we use them with any of the 4 basic connectives. We'll do this with tables that in the mathematical vernacular are called truth tables. The first connective that we'll see is the negation, and we'll use this symbol to denote it. Let's say that K represents the proposition Pikachu is a Pokemon. What's its truth value? Well, because Pikachu is in fact a Pokemon, the truth value of K is true, which we will represent with the number 1. Because we're talking about negation, this expression here means Pikachu is not a Pokemon. The truth value of this is totally false, which means that the number we'll assign to it is 0. Now let's see what happens if we take a false proposition and we negate it, for example H, that represents Hedwig is a Pokemon. Harry Potter and Pokemon fans will not argue against assigning this proposition a 0 value. If we deny it, then not H means Hedwig is not a Pokemon, and its truth value has changed to being true, that is, 1. Be aware that this is not only true for the propositions in this example, but for every proposition, and that's why we can always use this table when dealing with propositions and negations. Thus, if the truth value of a proposition P is 1, then the value of not P is 0, and if the value originally was 0, then the value of its negation is 1. The next connective we'll see is the conjunction, whose symbol for us will be this one. It is usually read and interpreted like the word and in English. Thus, let's say that D represents the proposition Oddish is a Pokemon, and K, just like before, represents Pikachu is a Pokemon. Notice that both of these propositions are true, and that D and K is read Oddish is a Pokemon, and Pikachu is a Pokemon. What's the truth value of this? Your intuition might be telling you that the whole expression is true, and in fact, it is true. So the conjunction of 2 true propositions is true. What happens when we conjugate both a true and a false proposition? Taking our previous example of Hedwig is a Pokemon by H, what's the truth value of H and K? This is, what's the truth value of the sentence Hedwig is a Pokemon and Pikachu is a Pokemon? Well, the experience with our language can give us the intuition with the answer. It's false! Moreover, check that if we change the order, the truth value remains the same. Pikachu is a Pokemon and Hedwig is a Pokemon is still false. Hence, the truth value of P and Q, when one is true and the other is false. Finally, let's say that S represents the sentence Twilight is a Pokemon, which is false. Then H and S is saying that Hedwig is a Pokemon and Twilight is a Pokemon, and neither of these propositions is true. We can see that the truth value of H and S is false. Therefore, if two propositions have truth value 0, the conjunction of them is 0 too. The third logical connective that we'll see in this video is the disjunction, with symbol like a V and usually read like OR in English. But here we have to make a warning. In English there are several uses for the OR. The conditional one that moms use when they say either you eat your vegetables or there won't be ice cream. That might be changed by if you eat your vegetables, there will be ice cream. The exclusive one that people use when they offer two options but you can only take one, just like in the sentence either you are short or not. And the inclusive one, where they give you two options but it is implied that any of the two could be true, for example, tables are square or round. The most common in math is the last one, which we'll analyze here. Based on what we just said and the experience with our language, what truth value does the proposition K or D have? That is to say, Pikachu is a Pokemon or Oddish is a Pokemon. Actually, both are true, and it is not hard to assign the value true to K or D. Let's see what happens if we have a disjunction of a true proposition and a false one. For example, K or H, interpreted as Pikachu is a Pokemon or Hedwig is a Pokemon. Well, 1 out of 2 has value 1, and that should be enough for us to assign the value true to the whole disjunction. Finally, if both propositions are false, as in H or S, that is, Hedwig is a Pokemon or Twilight is a Pokemon, we will assign a 0 value due to the fact that neither of the propositions is fulfilled. To sum up, if in a disjunction the two propositions that conform it are true, then it is true. Similarly, if just one of the propositions is true and the other one is false, then the disjunction is still true. And finally, the only way in which a disjunction can be false is for both propositions that make it up to have the value false. The last logical connective we'll see is the most controversial of the four, the implication. When this was invented, people were trying to model the kind of reasoning that we do commonly, such as if it rains, the grass gets wet, or if you study hard, your head is going to explode. However, by trying to use it as a connective similar to the conjunction and disjunction, the final implication that we created allows for weird lines of thought to be true, such as if our feet have arches, then our planet is round, or if the grass is green, the sky is blue. The big difference between the implication that we'll study called material implication and the implications commonly used in our language is that these last ones are more like rules imposed by somebody. Nature imposes that if it rains, the grass gets wet. Moms enforce the idea that if we eat our vegetables, then there will be ice cream. And some other stuff are a rule by definition, like the fact that if you're a married man, then you have a partner. That's why you must be clear that the things that we're studying here are not exactly the same that we use in our everyday communication. Without anything else to say on the matter, let's impose some rules on the material implication to get its truth table. First of all, it should be clear that true must imply true. If that weren't the case, then our everyday reasonings might be false and we don't want it. Therefore, if P is true and Q is true, then the whole implication P implies Q is true. As a second rule, we'll say that from something false we can deduce anything. That is to say that if the first proposition or premise is false, then any conclusion we might get makes the whole implication true, like every conclusion. To justify this, we can say that starting from a false hypothesis is like saying, let's use our imagination, and in that fantasy world, everything is possible, hence everything is true. There's a Mexican popular saying that goes like this: if my grandmother had tires, she would be a bicycle. It sort of gives us the idea of this false hypothesis thing. So, in an implication, if the antecedent P is false, then you don't need to check the consequent because the implication is already true. Let's consider the last case when the antecedent is true and the consequent or second proposition is false. This is precisely what we do not want to happen, to derive false stuff from true stuff, and that's why this will be the only case when the whole implication will have the value false. To conclude, we can say that an implication P implies Q is false only if P is true and Q is false. In every other case, implications are true. Thank you very much for watching. If you like the videos, like, subscribe, comment, or share. See you next time.